say that we've got Chris Timpson with us today, who's from Brasenose College, Oxford. And Chris is, we're very lucky that Chris happens to be in Edinburgh at the moment, has very kindly agreed to give a seminar. And he's going to be talking to us about Timelike experimental metaphysics.
Good. Thanks, Mark, and thanks to Mark and to Michaela for the invitation to come and speak today. I've visited Edinburgh many times at the university, so it's a pleasure to visit another ancient seat of learning. Good. So, 2014, this year, is the 50th anniversary of an intellectual milestone. Anybody got any idea what I might have in mind? It's a physicsy milestone. So it happened in 1964.
CERN was celebrating something, but I don't know. I think CERN is not 50 years, is it?
No, no, certainly not. But it's not wholly unrelated to CERN genetically. It's 50 years of Bell's theorem. So 1964 marked the publication of Bell's seminal paper on essentially the impossibility of local deterministic hidden variable theories. So stemming from Bell's work, or the work stemming from Bell's work, is often described as, slightly playfully, experimental metaphysics. Why experimental metaphysics? Well, the idea is that by a relatively straightforward kind of experiment, and that always actually means a very difficult one, one can hope to challenge or test or indeed settle certain kinds of very broad natural science or possibly metaphysical questions. So, as I say, reflection on Bell's work, what Bell showed on the experiments to test violation of Bell's so-called inequality, is often described as experimental metaphysics because one's seeking to test experimentally the question of whether or not the world allows action to distance, instantaneous action to distance. This might be of interest to philosophers just because they're interested in the nature of causation and what metaphysics might go with causation, and whether there can be gaps between cause and event, spatial or temporal. And it's of interest to physicists, particularly because it bears on the question of consistency with relativistic theories, which is one of the cornerstones of modern physics. So Bell's experiment is often, experiments to test Bell's inequality are often called experimental metaphysics. Now this has to be taken with a little pinch of salt, of course, because we know that no purely empirical or a posteriori matter can on its own settle any a priori or necessary matter such as metaphysics. But on the other hand, you might say that any metaphysics worthy of the name needs to engage seriously with the content of science in general, and perhaps with physics in particular. Yet again, we know that experiments have no bearing on any theories that we might have, whether the more specific theories or the more general metaphysical theories. Experiments on their own can't bear directly on those things. We always need various kinds of theoretical assumptions in the background to interpret our experimental results, to draw conclusions about the truth or falsity or the likelihood or otherwise of the various more abstract or grander or deeper propositions we might be interested in. So experimental metaphysics is a phrase that should be taken slightly cautiously, but the general idea is that, and the remarkable thing that Bell showed us how to do, is how one might set up an experimental scenario where one is genuinely testing, pretty plausibly with very minimal theoretical commitments, a broad class of physical theories, a broad and interesting class of physical theories, all of which include this property of no action at a distance or locality. Sort of the take-home message so far with respect to Bell's theorem and the test of Bell's inequality is that so far experiment is agreeing with quantum theory, because of course quantum theory predicts violations of Bell's inequality, and against the idea of the satisfactoriness of local theories. So if a local theory, so Bell set things up as follows. If we consider this as time evolving over here, and we've got space over here, we imagine doing a measurement here and a measurement here. If we believe that relativity holds, then we think that the causal structure will have the following kind of shape. We'll draw what are known as the past light cones of these measurement events here. And the normal understanding of what constraints on causality relativity imposes is that all causes of an event in here had better lie on or within the past light cone of this region of space, and similarly over here. So you set up an experiment where you have a lab located here and a lab located here, You create some special state of a pair of particles here, you send one off over there, you send the other off over there, you make a choice of measurement direction over here, choice of measurement direction over there, and you say, if locality holds, that is to say, if it's in fact the case that all the causes of events in this region lie within this backlight cone, and all causes of this events in this region lie in that backlight cone, then you derive a certain inequality, a Bell inequality, regarding the statistics you'd see for these various measurements you might perform, and in fact, this particular algebraic combination, which has got to be less than 2, it turns out. You do the experiment, and you find that in fact, the correlations we see between here can be as much as 2 root 2, so up to 1.4 times that. So nature violates the Bell inequality, and we conclude that it can't be the case then that all the causes of events here lie in the backlight cone up here. So we see correlations between here and here, and the thought is there must be some direct action to distance between the two. That's roughly speaking. There are some things you can do to tidy that up, and some quibbles one could raise, but broadly speaking, that's the picture there with Bell's inequality and tests of it. Is that okay so far? Okay, good. So this is space-like experimental metaphysics. Space-like because we describe these things because they're spatially separated from one another, and it's not possible for a normal causal process or something going at or less than the speed of light to go from here to here. We say these two regions are space-like to one another. What I want to talk to you about today, partly in homage to Bell 64, but also just because it's intrinsically interesting, it's one of the things I happen to be thinking about at the moment, is time-like experimental metaphysics, where you apply much the same mathematical reasoning. In fact, it's the identical mathematical reasoning. But we're looking at measurements, we're going to be considering experiments which involve not measurements on spatially separated systems, different kinds of measurements on spatially separated systems, but measurements over time on a single system. So I have my system prepared in the lab here. It evolves over time, evolves over time. And I can consider doing a measurement at this point, I can consider doing a measurement at this point, and I can consider doing a measurement at that point. And then we're going to draw some conclusions, hopefully, regarding these experiments of a grand metaphysical nature, or at least moderately interesting metaphysical nature, or at least moderately interesting. Okay, lots of people have been working on this at the moment. Here's just a bunch of the more recent experimental papers of people working on this kind of stuff. There's lots of them, doesn't really matter who they are. Let's get back to the progenitors of this, this reasoning. So this is a paper by 2 chaps called Leggett, well, one chap called Leggett and one chap called Garg. And this is a paper in 1985 in Physical Review Letters. And it sets out what they want to test. And they're just going to appropriate Bell's mathematics, perfectly respectably appropriate Bell's mathematics for a different purpose. Looking at experiments arranged over space, over time at the same space as opposed to at the same time, as it were, at different spaces. Here is what they set out as their rationale for thinking about these things and for deriving the inequality, which would be called the Leggett-Garg inequality. Though they didn't call it that, of course, other people called it the Leggett-Garg inequality. This is what what motivated them. They said, look, quantum mechanics has been around for a long time, despite, it's been around longer now, but in 85 it was, despite 60 years of schooling in quantum mechanics, most physicists have a very non-quantum mechanical notion of reality at the macroscopic level, which implicitly makes 2 assumptions. The first, assumption 1, this is the big one, this is the piece of metaphysics we're going to be interested in testing. Macroscopic realism. This states that a macroscopic system with 2 or more macroscopically distinct states available to it will at all times be in one or other of those states. The second assumption, which they argue in more or less depth later on, they think naturally follows from the first, is that non-invasive measurability at the macroscopic level is possible, as is to say it's possible in principle to determine the state of a macroscopic system with arbitrarily small perturbations on its subsequent dynamics. That's actually a pretty natural way of thinking if you're born and brought up, as we all are, in a classical world of classical physics. But Leggett and Garg's point is that, as they say, if you extrapolate what quantum mechanics says about things directly in the straightforward, the natural way, then quantum mechanics will deny these claims. And here we're in, if it's not obvious already, here we're in the realm of Schrödinger's cat. Okay? So Schrödinger's cat is an example of how quantum mechanics would seem to predict, does predict, or would seem to predict the failure of macroscopic realism. So cats can be either alive or dead. Usually we think those are the only two ways that they can be. I suppose they can be slowly dying. Let's put vagueness to one side. So ignore all vague predicates for the purposes of a subsequent discussion. Cats are always either alive or dead. They're one or the other. However, quantum mechanics suggests that if you create one of these nefarious potential murdering devices where you have some atom which is going to decay, some Geiger counter which is going to detect the decay, which is going to set off some killing apparatus, then because the laws governing the atomic decay are themselves quantum mechanical, then the quantum mechanical possibility of superposition between distinct ways of being can be amplified up to the macroscopic level, and you can end up with your Schrodinger's cat being in a so-called superposition of being alive or dead. It's neither one nor the other. It's in some certain sense, some novel sense, in both. Now, our classical intuition tells us that cats are always alive or dead. Macroscopic realism is the claim that things like cats are always alive or dead, notwithstanding what quantum mechanics might have to say about the matter. Now, it's true that we always see cats as being alive or dead, but it doesn't necessarily follow from that cats always are alive or dead, that this junction exhausts the possibilities. Because it could be that when we're not looking at them, they behave differently. Okay, so it could be that every time we look, and by look here, I mean this is a generic term for observe in any kind of general way, I don't mean specifically visual perception. Whenever we look at something that might behave in a certain kind of way, it doesn't necessarily follow that things of that kind always behave in that way when we're not looking. What Leggett and Gard did was to say that, well, we can test this proposition, that essentially the classical worldview holds by deriving an inequality which is a time-like version of a Bell inequality. Starting from this macroscopic realist proposition and using this idea of non-invasive measurability. Okay. Is that clear enough so far? People reasonably happy? I mean, the details will come out as we go along. Good. One thing we might note at this point is, or one thing we might want to flag at this point, is the question of how apposite this name here is. Macroscopic realism. We know, of course, that a rose by any other name would smell as sweet, but equally well, aptly chosen terminology can often affect how people think about things. And for those who are versed in the philosophy of science, you might say, well, I'm not entirely sure that this characterization of macroscopic realism is what I would mean by a general claim of realism about the macroscopic. Okay, so this is a rather specific claim about how things have to be. And of course we can just stipulate that what we mean by two words, macroscopic realism and realism when conjoined is this. But an interesting question, if we're looking to do experimental metaphysics, is that we really have an interesting, or as interesting as we think, a metaphysical proposition in our grasp. So you might think that what violation of a Leggett-Gard inequality by experiments on secretly macroscopic bodies shows was that realism is false. And one would take that to be really quite a marked and direct metaphysical conclusion. In fact, much more marked and direct than Bell's conclusion about failure of locality, according to quantum mechanics, and indeed according to the world. But is it obvious, and perhaps I'm going to suggest it isn't obvious, that macroscopic realism is here defined as equivalent to realism about the macroscopic? And that's for a very simple reason. And we can build up to that reason by saying, okay, it may be true that, that most physicists, despite 60 years of schooling in quantum mechanics, have this notion of non-quantum mechanical notion of reality at the macroscopic level. But it doesn't follow that that's what, as it were, a non-naive view about what is going on, really going on at the macroscopic level is. So it could just be that they're mischaracterizing how one ought to think about reality in the quantum mechanical realm. And what might lead us to think about that more strongly is something I want to push with a counterweight slogan to try and counter the strength, the powerfulness of conjoining macroscopic realism and stipulating it to mean what Leggett and Gard stipulated that it meant. And here's the simple slogan. look, there's nothing realist about denying the existence of superposition, whether it's macroscopic superposition or otherwise. Okay. If Schrödinger's cat really is in a superposition, that doesn't show that realism is false. It just says that, well, the world is not behaving classically. But who said that all ways of being realist are classical ways of being realist? That's just something to hold in your mind for the moment. We'll come back to develop that in more detail as we proceed. What I want to do now is explain what in fact Leggett and Gard proposed and how they wanted to test this proposition, macroscopic realism, and the nature of the inequality they derived. So the next 4 slides are all in your handout, so you can refer back to them as we progress through the talk. Okay, so here's the setup for the inequality. So here for some reason I've rotated this around. Here we've got time is now going in this direction in space. Well, not necessarily space. Anyway, time's going on that direction. And we're here considering 3 distinct measurements that one might make on a single system. And we could suppose that this is a macroscopic system because after all that's what ultimately the doctrine that Leggett and Gard want to test. Being practical kinds of people, we realise that actually subtle tests of physical phenomena and the behaviour of macroscopic objects in particular are pretty tricky to do. So what people are actually doing, so those 8 or so people I showed you on the second slide, they're not actually doing tests of this inequality on macroscopic objects. They're doing them on various microscopic or slightly bigger than microscopic objects with the hope of scaling up to larger systems in the future. What Leggett and Gard had in mind as the kind of system they were interested in was a piece of, where they thought this experiment might be interestingly performed, was a piece of superconducting material, a ring of superconductor, essentially like you have in an MRI scanner or something like that. In a ring of superconductor, you can have an awful large number of charge carriers, all behaving prima facie, or at least most straightforwardly described in a purely quantum mechanical way. You can have the current all going around that way, or you can have it all going around that way, or like Schrödinger's cat being a superposition of both, you can have them going around both ways at the same time, which is not to say that there's no net current flowing. But the experiments on the superconducting rings didn't turn out to be practically feasible straight away, so people are working with smaller systems at the moment. To a certain extent, the logic that I'm most interested in here doesn't actually rest on the question of whether macroscopicness is in play or not. The basic logic about what's going on with the Leggett-Gard inequality and whether violation of the Leggett-Gard inequality really would show that some interesting substantive proposition about how the world is true or false. Doesn't really matter whether it's micro or macro, so just bear in mind that these, we could be thinking about macroscopic objects, but it needn't be a matter what size they are to begin with. It gets most interesting when you're macroscopic, but the logic doesn't really affect it. So here's the setup of the experiment that they proposed. So we've got one system, and we're supposing that there, I'll just use the word macroscopic, supposing there are 2 distinct macroscopic states which are available to it, which we can label with a plus and a minus here. This needn't be a spatial separation, indeed, between the 2 different states, though it could be. In general, there are all kinds of distinct properties that systems might have, some involving differences of spatial position and others not. We're just imagining that there are 2 distinct states which a system could be in. The macroscopic realist is going to say, and there are only those 2, they've always got to be in one or the other, there's no funny business of Schrödinger cat-like superposition going on here. And we can imagine performing a measurement at time 1, at time 2, and at time 3 of whether the system is in that state or that state. And if it turns out to be in a plus state, I can give that a numerical number of +1. If it turns out to be in a minus state, I can give a number -1. And then I can realise that certain very simple algebraic features hold. So I can when I run my experiment, I can note down, say, what I get as the result of the first measurement. So suppose I get a +1 as the result of the first measurement. Then at the next, as this evolves over time, I do the next measurement. Then, well, it could be that it just stays in the same state, or it could be that it flips over to the other state. And so we could get a +1 or a -1 for the next measurement. And then suppose we get a +1 again, it could carry just straight on and be another +1, or it could flip to the other one. So I imagine I've got a set of values. These are all the possible values when I start with +1 here. These are all the possible values when I start with -1 here. And because these are the actual outcomes of actual experiments that I actually performed, there are facts about what the values of these are on any, once the whole experiment's been run. So I can just take algebraic combinations of these in a certain kind of way. And this is the one that Leggett and Garg suggested, and they did this because it ties up to the mathematics in Bell's theory, but that doesn't really matter. So they say, take the value you get for the first experiment and multiply it by the value you get for the second experiment. That's Q1, Q2. Then add to that the value you get from the second experiment and multiply that by the value, add to that the product of the outcomes of those two, and then add to that the product of the outcomes for those two. And we can just see very straightforwardly from this table that this quantity here, the maximum value that it can take is +3, and the minimum value it can take is -1. And in general, you can imagine doing this experiment over and over again. So on each run of the whole run of the experiment, I'm going to get a quantity of Q out at the end, which is either 3 or -1. I can imagine doing this over and over and over and over again, and then taking the average of that. That's what these angle brackets here are going to mean. So that average, when I do over the ensemble of repeated runs of the whole experiment, is going to be between 3 and -1. Okay, now this is basically straight algebra so far. This isn't anything particular to do with quantum mechanics, and this is completely general. So for any theory which allows there to be definite outcomes for these measurements simultaneously, and that's pretty much going to be all theories that one might like to consider, this inequality is going to hold. So far, nothing interesting here though. But then we can note the following. If we make the two assumptions that Leggett-Garg want us to consider, namely the big one, macroscopic realism, and then the subsidiary one which they suggest follows from it, namely non-invasive measurability, they say that something interesting is going to happen. So if in fact it's the case that my system here that I'm doing experiments on can only either be in that state or that state, and if because of that it's possible to do a measurement which is non-invasive, which recall is a measurement which doesn't affect how the system is going to behave in the future, then you can see pretty straightforwardly that it's not going to matter to the statistics I get overall whether or not I do the first experiment. Right? So if I calculate the product Q2, Q3, if it's the case that these two properties hold, and particularly the non-invasive measurability one, then the statistics I get are the same. What it is for the measurement here to be non-invasive is for it not to disturb the evolution of the system. So it just doesn't make any difference to the overall statistics when I go to calculate something like this, whether or not I do it. So we can represent that by saying that the values that you get for the product of 2 and 3 when I just do the second and third measurement are the same as if I did all 3 measurements. And then you can see how this is going to go. Similarly, if I can do this one in the middle, non-invasively, then I should get the same statistics when I calculate that times that, if I did all 3 as if I didn't. And then we also notice that here this is things evolving over time. If you think I should be able to causally affect things in the past by things I do in the future, which is a pretty plausible and maybe essential conclusion, and it ought to be the case that the statistics I get for this pair are the same whether or not I do this final measurement. So then these 3 hold. And what that means is that, so here I've got a case in which I do all 3 experiments together, and then I consider doing that one together with that one, so call that experiment big Roman 1. I do that one with, we do that one with that one, call that experiment 2. And then I do that one with that one, call that experiment 3. The statistics that I get when I just do 2 of the experiments at a time, that should also be greater than or equal to -1. So the expectation value when I combine, you can't see this, can you? The expectation value when I combine the results for this experiment, so expectation value for Q1, Q2, when I only do measurement 1 and measurement 2, plus expectation value for Q2 and Q3, when I only do 2 and 3, plus the expectation value for Q1, Q3, when I only do M1 and 3, should also be bounded by this. And that's a highly non-trivial result, right? The equation here just holds as a simple algebraic fact because I'm doing each of the measurements. That it should hold when I do that in one set of experiments, and then do that in another set of experiments, and then do that in a third set of experiments, is a highly substantive and non-trivial claim. And it only follows if these properties here hold. And Leggett and Garg say, look, these properties here are going to hold, because of macroscopic realism and non-invasive measurability. So if it turns out that I do an experiment like this, or rather, I do these three sets of experiments, and then when I combine their results in the appropriate way, I get a result which goes below -1, then I'm showing that macroscopic realism and non-invasive measurability can't be true, because if they were true, then they couldn't get below -1. Turns out that it's possible quantum mechanically to get below -1. It also turns out, in all the experiments that have been done to date, you can get below -1 here. So far, the world is in agreement with quantum mechanics on this. So the message at this point might be, for at least those systems, and indeed they're pretty small systems, but on the other hand they're not totally tiny systems. All those systems are so far going with quantum mechanics and showing that our perhaps naive macroscopic realist conceptions of how things ought to behave are false. Okay. Is that okay? Everyone's on board? Yeah? Fine. Let's think about what's going on here a little bit more carefully. And let's come back to this question that I mooted earlier, the question of whether macroscopic realism is really aptly named or whether it's sneakily named, the extent to which macroscopic realism is genuinely realism about the macroscopic. So, of course, people might mean different things by realism, okay? And one's free to define one's terms in the ways that one wants, but this is, of course, is how philosophers of science think about what realism is. So I guess this will be completely familiar to everybody. So realism in the philosophy of science is the doctrine that, by and large, theories aim to give us literally true descriptions of what the world is like, both in its directly observable and its non-directly observable features. Moreover, that the empirical success of theories gives us prima facie, defeasible, but prima facie good reason to believe that our theories are true, or at least approximately true. And moreover, that the statements of our theories, or statements indeed in general, are true or false in virtue of mind-independent facts about the world. Okay, that's just standard definition of realism in the philosophy of science, I take it. Now, as applied to quantum theory, what would realism entail? Would it entail the kind of view, A1 and A2, that Leggegaard mentioned earlier? Well, this is what a philosopher of science would think realism about quantum theory would amount to. It would be the claim that we've got a formalism here of quantum mechanics, we've got actually a very detailed formalism, and if you're going to be realist about that formalism, if you're going to be realist about quantum theory, you better stipulate which bits of that formalism are supposed directly to represent the world. Okay? At least some part of it, and possibly quite a substantial part of the formalism of the equations, should be directly representing physical facts about the world. And moreover, we take quantum theory to be a fundamental theory, or at least a candidate fundamental theory. So it's supposed to be describing everything in the universe at the fundamental level. So we should be trying to describe the world seamlessly and as a whole. We can take the whole thing all at once, and there's no sort of breaking up into domains, and some of which the laws hold and some which don't. Okay, this would be a standard realist picture, what Nancy Cartwright would call a fundamentalist picture. So perhaps Nancy Cartwright would disagree with this conception of what realism is, but as a starting point, we can state that this is a standard view in of realism about quantum theory. And as a corollary of this conception of what it would be to be a fundamental theory, it ought to be the case that any reference to observers in the theory ought to be eliminable, right? So especially talking about observers, parochial beings such as ourselves, really shouldn't play any fundamental role in the theory, because we are not important constituents of the universe from the point of view of physics. We're interesting from our own point of view, but the universe doesn't really care for us very much. Well, no, that's not quite right. It's not that it doesn't care for us, but there's no fact either way whether it cares for us or not. And I call this an unassuming physicalism. We should be able to model ourselves, we should be able to model observers in the theory, explain how observers are constituted by smaller things. Insofar as we need to talk about observers at all, we ought to be able to give a story about how they're constituted by stuff that the theory deals in and obey the laws that the theory stipulates. Okay. So this would be a standard desiderato, or indeed stipulation, is what it would be to be realist in quantum theory. And then, of course, we have various examples, which people may be familiar with, of out-and-out realism about quantum theory, the simplest kind. You can have an Everettian many-world kind of view, which just takes a straightforward realism about the prime central mathematical component of the quantum description, namely the quantum mechanical wave function or quantum state. They say there is a quantum state for the world as large, for the universe at large. That quantum state directly describes a feature of the world. And what we see around us are essentially branches within this overall quantum state. We can have various kinds of hidden variable theories, such as the de Broglie-Bohm theory, which agrees with the Everett theory that the quantum mechanical wave function describes a wave-like thing in the world. But the primary role of the wave-like thing, on their view, is to push around various hidden variables, specifically for creatures like ourselves, push around, to govern the evolution of the locations of the things which constitute us. So all particles have a position on this kind of view, and they're pushed around by the wave function. Or we can have a theory like the Ghirardi-Rimini-Weber theory, or so-called dynamical collapse theories, where again you have the wave function describing literally some wave-like thing in the world, but in order to get around Schrödinger cat-like problems, it says that, well, some of the time you evolve and have these nice superpositions, and other times you have a jump to one way of being versus another way of being. So these are standard developments of the realist idea in quantum mechanics. So this would be, if you like, standard quantum mechanical realism. And then you can have interesting arguments about which of these one might prefer. But they're all versions of quantum mechanical realism. Now, how does this kind of conception about what realism in a quantum world might be relate to the kind of things that Leggett and Garg were inviting us to think about? Well, the picture is rather complex and puzzling. And this is sort of an interesting thing for philosophers, and this is sort of where I got into the debate. So we've got some simple things we can say, but the overall picture is puzzling. So now the average interpretation does violate the Leggett-Garg inequality, but it is realist, and moreover it does account for the determinate features of the macroscopic world. This is broadly agreed on, that at least it does that. So there's a sense in which, well, look, Everett seems to be realist, and at least that it macro-realist, in at least that it delivers us realism about the macroscopic. The de Broglie-Bohm theory again violates the Leggett-Garg inequality. It's a theory which again has superposition in the wave function. Yet here, and in separation from Everett, or distinction from Everett, it is the case that macroscopic variables do take on definite values at all times. So it's a theory which does satisfy the definition of macroscopic realism. And that kind of case is particularly troubling for the story that Leggett and Garg are presenting, because here we've got a theory which is macroscopic realist by their lights. It's always the case that when you've got two macroscopically distinguishable states, the world's either in one or the other, according to the de Broglie-Bohm theory. And yet, you can violate Leggett-Garg inequality in de Broglie-Bohm. So something seriously wrong has happened at some point. And then turning to theories like GRW, well, this is a funny one again, because sometimes it will and sometimes it won't violate the Leggett-Garg inequality. But it's certainly a realist theory. And it will always be the case that the macroscopic variables and macroscopic properties we generally care about, namely coarse-grained positions of things, will come out determinate. So something very funny is going on in the interplay between the definition of macroscopic realism, what might otherwise take to be realism about the macroscopic, and what is shown by violation of the Leggett-Garg inequality. So, going back to Leggett-Garg's original opening, I think this does give some cause to worry that really partly what's going on here is that we have got too naive a setup for the problem. Which is not to say that there isn't a problem here which can be tightened up and made more interesting. Okay. So, part of what's going on, I should have said at the beginning that all this stuff I'm talking about is joint work with Owen Moroney at Oxford. One of the things that we diagnose as having gone wrong with the standard debate in Leggett-Garg and with their setup at the beginning and some of the subsequent literature is that unlike what goes on in the Bell scenario, it's not the case that discussion of Leggett-Garg has been set up in an adequately model-independent way at the beginning. In our minds, Leggett-Garg's starting point is itself already too closely tied to quite a straightforward way of thinking about quantum mechanics. But the powerful thing that came from Bell, the reason why you might plausibly call it experimental metaphysics as opposed to just looking at what quantum theory does, is that Bell manages, by setting up his experiment and setting up his inequality, he manages to rule out a broad class of theories, which includes, well, he's constraining a broad class of theories which includes quantum theory, but is not restricted to it. So he ends up with, as it were, a model-independent characterization of what a whole broad set of theories satisfying some natural properties ought to be like, and then sets up an inequality which can be experimentally tested regarding that. And we feel that nothing parallel has yet been set up in Legate-Garg. And so what we've done is to set that kind of thing up. Mark, how much longer have I got to talk about? 20 minutes? 10 minutes?
Yeah.
Okay, so how might one seek to make the discussion a little bit more model independent, to get further away from quantum theory, so we can hope to delimit the clear and natural and compelling class of theories which we might then put up for experimental test. Now, I mentioned a couple of times, but haven't explained yet, why Legate and Garg thought that non-invasive measurability should follow from macroscopic realism. Okay, so that might have been something that's worried you so far. So part of the thought here, but not the whole of the thought, though I think there's ambiguity in Legate and Garg's thinking, is simply the following. Okay, we're used to the idea that the big things we see around us are made of little things. And we're used to the idea that by and large, when we observe some macroscopic object, it could be the case that we're affecting the microscopic happenings in front of it. So when I'm seeing the table, it is the case that photons are bouncing off it and going into my eye. So it is the case that some microscopic features of the table are being affected by my being in a causal and a perceptual relationship to it. At least in this kind of world. But we're not affecting the macroscopic properties. Right? So interacting with a macroscopic system might well change its microscopic features, but typically we think not in such a way that we're affecting its macroscopic features. Okay, so that's a sort of a prima facie plausible view about why, if we have macroscopic objects being in different macroscopic states, we might be able to observe them and not change their macroscopic features, even if we change their microscopic features. And then moreover, one might think that, well, the kinds of little changes that are involved in the microscopic, which don't push us out of the macroscopic state that it's in, those changes may not be such as to lead to changes in the future evolution of the macroscopic state of the table. Okay, one might plausibly think that. But of course, we haven't actually checked that much in detail. And part of what's going on in Legate-Garg experiments is really to check whether that's so. So there's this kind of starting intuition. I'm going to draw a different picture on the board. There's this kind of starting intuition that we can think of there being a set of the ways, sort of maximally specific set of ways the world could be, the microstates of the theory, or in the terminology I'm going to use later on, the ontic states of the theory, the actual physical properties of the theory. I've got some space of states here, and it might be that actually this could be perhaps the space of states of the air molecules in this room. And in fact, all the air molecules, assume that classical mechanics is true, all the air molecules in this room have some specific positions, and so by my little cross here is to specify the point in this ontic state space, which corresponds to all the particles having the particular positions they do. Now, if all the air molecules are in fact right up in that corner, that might correspond to them being in a state down here. If they're evenly distributed, then there'll be quite a large volume of the state space where we could be. And from just measuring the volume, temperature, and pressure of the air in this room, I'm not going to determine which of these microstates I'm in. I'm just somewhere in this macrostate. So we can think of a macrostate typically as being something like a partition of an underlying physical state space. And then the thought is, when I've got perception here, I might push the microstate around somewhere in here, but I'm not moving myself out of this macrostate. Okay, so that's one idea to play around with. But the idea that Legate and Garg actually rely on is something more subtle than that. It's something called a null result measurement. So null result measurements are quite cute. I'm going to move over to the other board. So this is why they really think that the possibility of non-invasive measurement follows from macroscopic realism. So suppose I've got some measuring device, which I'm going to put here. There's a box which is sitting here. Some measuring device which is such that it only interacts with my target system if it's in the +1 state. Okay. And indeed, if this was corresponding to spatial separation, you might think you might have that if I just literally have a detector sitting right here, physically here, and not here. If it's in the -1 state, then this hunk of matter doesn't interact with that target system, so nothing happens. Okay. So we plausibly believe that various detectors of that kind exist. Now suppose macroscopic realism is true, and we say that, look, it's at all times, either it's the case that the target system is in that state, or it's in that state. Those are the only two options. Suppose I let the experiment run, and I don't see an outcome from that measurement. There are only two options. Either I was in the +1 state, or I was in the -1 state. If I was in the +1 state, my detector would have fired. Stipulate that it's a good detector. It always fires if you're in the +1 state. Since it didn't fire, I can infer that the system was in the -1 state, and I did that without interacting with it. Okay, so this is a null result measurement. I infer something about the state the system is really in without interacting with it. Because X hypothesis, for the sake of argument, it's only one or the other. If it were in this one, it would fire, it doesn't fire, so it must have been in that one. Okay. So if there exist detectors of that kind for the macroscopic quantities I want to measure, then you can see why, along with if macroscopic realism is true, it's always looking at one or the other, then if I don't have a firing here, I detect the state that the thing is in without interacting with it, so I can't have disturbed anything. Okay. That's a cute kind of argument, but the trouble with it is, for our purposes, is in the general case, why should one suppose that one has a measuring device which only interacts with your target system when it's in one particular one of the states? Okay, typically you'll have some background theory which tells you that, given that you've built your detector in this kind of way, and given the system you're looking at, these two are only going to interact when, in fact, this is in this state and not otherwise. But it really takes quite a lot of theory that one's assuming to tell you how your detectors are working. And what we really need for something that parallels Bell's inequality methodologically is knowing that our measurements are null result or non-disturbing or non-invasive. I'll clarify that distinction in a moment. Without having to assume any theory about how the detectors are functioning. We should just be able to show operationally, without assuming any background theory, that our detectors ought to behave like this. Because if we don't do that, then it's always open, and indeed might well be natural to say that, okay, look, you haven't shown the macroscopic realism is false, you've just shown that your detector is not a null result detector, so your theory about how the detector functions is wrong. The difference for the Bell case, when it was space-like, is that he had independent constraints coming from relativity to specify how things should be behaving. And there's nothing like that that's available in the case that Leggett and Garg want us to look at. Why should we believe in general that there exist, that there exist detectors which can do this, and B, that they're really non-result detectors? So, okay, so I said that. So we need to seek a model-independent characterization if we're to get into the realm of something properly like a Bell kind of experimental metaphysics. So here's how we might do that. Okay, we can just say something like the following. Just suppose that we identify a macrostate's operationally, so we just notice that various things in the world around us have particular properties which seem pretty insensitive to how we look at them. We stipulate, as I mentioned here, that there's some underlying space of physical properties which explain why things have the features macroscopically that they do. Call these things underneath microstates, or better, ontic states, and for historical reasons we denote them by lambda. So when I'm in here I have a particular value for lambda. And we can imagine that when we prepare systems in the lab in certain ways, because we only have relatively coarse control of them, what we're doing is preparing them somewhere within a region of the ontic state space, but we don't know exactly where. And in general, there may be, in fact, typically will be a probability distribution over here. So imagine an axis now coming out of the board, going up to 1, and we've got some probability distribution lying over this. That's supposed to be something like a normal distribution lying over this region here. So experimental preparations I can perform in the lab will prepare my target system of interest somewhere in a region of its ontic state space with some probability distribution over it. Call the probability distribution of the ontic states the preparation state for the system. Okay. Now, in specifying, in specifying rather precisely than Leggett and Garg did what one would mean by macroscopic realism, let's then consider the following species of behaviour of our ontic states, which need not exist in all theories, but certainly exist in many and certainly exist in classical physics. So let's say that we're interested in ontic states lambda, which are value definite. What do we mean by that? So an ontic state is going to be value definite for some measurement. If, given that the system of interest really is in that ontic state, then with probability 1, you would get the corresponding outcome. So suppose I'm going to do my measurement of whether something is in a left box or a right box. If the system has is value definite, its lambda is value definite for the property of left, then with probability 1, when I look in the left-hand box, or indeed when I look in the left-hand box, I'll see it there. Okay, so such a lambda is called value definite for a particular property. And indeed, there might be theories in which one's lambdas, or at least some of them, could be value definite for all properties one would look at. That would be classical physics. Okay, and we also want to capture the idea, really, that is the proper generalisation of Leggett and Garg's idea of macroscopic realism. We also want the idea that there's a parallel to another feature of our macroscopic experience, namely that different ways of looking at things give you the same answer. At least, if something is a good way of looking at something, if something is a good measuring device for a particular property, I could have a whole bunch of different devices which are good measuring devices for that property. They all better give the same response. And that's called non-contextuality. So the result you see doesn't depend on the method of measuring it. So really the idea of the realism that Leggett and Garg are gunning for, or at least they're interested in, is the idea that all of one's ontic states are non-contextually value definite for all macroscopic properties. So we can just call that feature macro definite. So that if you're in one of those, so all of the ways that the world could be are ways such that you'll definitely get one particular outcome of saying what the property that the system has, whatever way you measure that property. Okay. Now, there's an important set of preparations that we can perform, different ways that we can set our systems up, and it's what we're borrowing terminology from quantum theory we're going to call operational eigenstate preparation. So an operational eigenstate preparation is, if you like, it's an equivalence class of operational procedures you might perform in the lab, but it's a bundling together of all probability distributions over ontic states which are macro definite for the macrostate in question. So if I've got, if I can definitely prepare my system to be in the left-hand box, there might be lots of different ways I could do it. I could sort of throw it in clumsily, I might lay it in gently, I might put it in, heat it up and cool it down. All the different ways that you might prepare the system definitely to be in the box. If it's the case that any one of those operational procedures is such that with probability 1, when you do a subsequent good measurement, you're going to find a system in the box, then you've put the system into an operational eigenstate. So an operational eigenstate is an equivalence class of preparation procedures, all of which are guaranteed to give you a yes result when you measure that particular quantity. So that's the equivalence class of preparation procedures, or alternatively, a probability distribution over ontic states, each of which is macro-definite from the macrostate. Now we start going back to the beginning and looking at cats and finding that they're always alive or dead. We just find that the world, the states of the world are always determined one way or the other with respect to the macroscopic properties. And then a natural explanation for this fact, you might say, is, well look, there's just no way that the world could be which isn't one in which the ontic states are macro-definite. So that's a natural way of explaining why we always see things in one state or the other, because things always definitely are in one state or the other. And that's the proposition that we want to test, Leggett and Garg want to test, now set up in a slightly more general framework. So going back to the Leggett and Garg setup, we have our three measurements. We should distinguish between what's operationally available to us, namely the question of whether or not a measurement that we might perform doesn't disturb the statistics that we expect to see. And so we call that operational non-disturbance. And there's a very much stronger proposition, which is what null result measurements deliver us, namely non-invasiveness. That is to say, the measurement tells us the value of the property that the system has, but it doesn't affect the ontic state of the system at all. So this is massively logically stronger than this one. Okay? And Owen Moroni has a theorem that actually all that's required for a Leggett-Garg inequality to be satisfied is not this very strong thing, but only this much weaker thing, which is silent about the actual behaviour of the measuring device on the ontic states. It's just enough that whatever's happened to the microstates, the ontic states underneath, I'm not disturbing the statistics that I see at a coarse grain level. Okay. So, Leggett and Garg, by appealing to null results, if it's really the case that you have this kind of setup you had over here, that we have no interaction with the system, then we're not disturbing its ontic state. That's the strong sense of non-invasiveness. But all that's required to derive the Leggett-Garg inequality is this much weaker thing. So, if we have some scenario in which the Leggett-Garg inequality is violated, we better have some good reason for thinking that in fact it's non-invasiveness that fails, and thus macroscopic realism that fails, given non-result measurements, as opposed to merely it's being the fact that our measurement is operationally disturbing, which is just silent about whether or not every ontic state is a macrodefinite ontic state. So how might one approach things operationally? We're nearly at the end, by the way. So here's what we can actually just do directly by operational procedures in the lab, which doesn't assume too much theory. So suppose I just start off by preparing my system in some state. I've called it an L state here, so we're in the left-hand box. So I prepare my state definitely in there. So it's an operational eigenstate for L. And then, it could be that once I've prepared it here and I do some later measurement, it could be that it's just given the natural time evolution that happens, that there's some chance of it popping down there. So just restrict the time evolutions that you're going to allow to happen to ones which keep it in the L channel, the +1 channel. And then I can perform my measurement, which I hope to be my putative null result measurement. Maybe we should put MNR here, so for null result, that should maybe be in scare quotes, because what we're trying to establish is whether this is something which plays the kind of formal role that the null result measurement is supposed to play. And what I can do is then see whether, given that I prepared this in the L state, I do this measurement. I'm definitely, because this is a good measurement, I'm definitely going to get a yes, it's in the +1, i.e. L state here. And then I can imagine doing a second measurement by any old measuring device that's a good measurement. It doesn't need to be a non-disturbing one. And I can check whether or not the probability distribution for left versus right here is affected by whether or not I do that measurement, given that I prepared it definitely to be up here. So the significant thing is here, I've prepared this definitely in such a way that it's up here. The ontic state is one which is macrodefinite for the L value. I prepared some particular probability distribution over ontic states, which are all macrodefinite for L. Okay, good. Now suppose in fact that the distribution for left and right outcomes isn't affected by this. Then I've shown that that measurement is definitely non-disturbing when the system is in an operational eigenstate of L. So it's in the preparation state where it's definitely going to say, yes, I've got the property L. What we can then do is go back to allowing general time evolutions of the system. So it may well be that it jumps from the left channel down to the right channel before it hits the first measuring device. But what I'm going to do is, again, going back to sort of null result measurement. So I've established that this fellow here is non-disturbing when I'm definitely in this state. If it's possible that the thing went down here, whenever I get a firing over here, I just throw that run of the experimental data away. And I just keep the experimental data where I get a +1 outcome here. And then we should think, okay, so I've shown that the measuring device is non-disturbing if I'm definitely in the L state, if I've prepared it in the L state, the L preparation state. So it ought to be the case now that the Leggett-Garg inequality is satisfied, because I've shown that that first measurement is non-disturbing if I prepared it definitely to be in the L operational eigenstate. So then, if it turns out, as indeed all the experiments, actually there's only been one experiment that does anything like this, by my colleagues in Oxford, I should say. If it now turns out that this Leggett-Garg inequality is violated, we're going to be left very confused. Because we'd shown that, well, if the system was prepared such that it was definitely in the L state, so it was an L operational eigenstate, then the measurement is non-disturbing. The measurement is disturbing. So, should we conclude now, and it seems there's a big pressure to conclude this, since we conclude that, well, it can't be that it was in the right state because we threw away all those runs and we got a right outcome here. So we're inclined to think, well, it couldn't be in the L state, the L preparation state. Definitely wasn't in the R preparation state. So there must be some other state that it was in, which is not macro-definite for the macroscopic quantity being measured, i.e. macroscopic realism is false. That looks like quite a compelling argument, given where we got to. But we shouldn't conclude that, okay? And this is where, as it were, all the action takes place. Now, because it could instead be that what's happened under the general evolutions that we allow, and now it's possible for the state to evolve into a state where there's a non-zero probability for a positive outcome for R measurements. It could well be that the system is still in some ontic state, which is macro-definite for L. But just as part of a state, that is to say a preparation state, a distribution over ontic states, which is not an operational eigenstate for L, and thus is one which we simply haven't checked whether our putative non-disturbing measurement was indeed non-disturbing. Okay, so we only checked that it was non-disturbing when we prepared the system in an operational eigenstate for L, that is to say a state, a preparation state, a probability distribution over ontic states, such that we're always guaranteed to get a +1 outcome for here. But it doesn't follow that we've checked non-disturbingness for those things, that we've checked non-disturbingness for all macro-definite for L states that there could be, preparation states or ontic states. So, violation of the Leggett-Guardian equality only tells us either that macroscopic realism is false, or it's false that every probability distribution over macroscopically definite ontic states is a mixture of operational eigenstates, a probabilistic mixture of operational eigenstates, which is a very much weaker conclusion. Now it turns out that there are two, and I think only two, ways in which this could be so. Let me draw a little bit of a picture here. And both turn out to be ones that are actually familiar in the foundations of quantum theory, but it's nice to, or there are concrete instances which are familiar from the foundations of quantum theory, but it's nice to see how the space of possibilities carves up. So, we're still within the realm of macroscopic realism. So when I draw my ontic state space for the world, every state that's in here is one which is non-contextually value definite for our macroscopic quantities. So everyone says, yes, you're definitely either L or definitely either R. Okay, every single one of these states are, wherever I am in this ontic state space. And so let's just draw a line down there and say, let's say that every state in here is non-contextually value definite for an L outcome. Every state in here is non-contextually definite for an R outcome. I've got to be somewhere over here or over here. Good. And then when I'm preparing states, I'm going to describe case one now. When I'm preparing states, when I'm preparing systems, what I'm preparing is a probability distribution over the ontic states, right? So let me draw that in green now. So I've prepared some probability distribution over the ontic states. Now, it could well be, so the case one we want to consider is a case in which every single ontic state which is macro-definite for L is an ontic state which falls under the support of, which means to say falls underneath the probability distribution, has a non-zero value of probability distribution of an operational eigenstate preparation. So the operational eigenstates give me some probability distributions over this space of states, but not necessarily all of them. So it could be that the operational eigenstates give me a family of probability distributions, say, which maybe sort of look like that or like that. But there could be other probability distributions over here, which are something like that. And I'm never going to get one that looks like that by mixing together these ones. And it might well be that if my system has a probability distribution like that, then my measuring device doesn't affect the shape of that probability distribution. My null-result measuring device doesn't affect the shape of that probability distribution. But it does if I have a shape like that. Why could that be? Because it could well be that my measuring device twiddles my states around under here, but in a kind of a symmetric way, which doesn't show up. So I still have the right number of states falling under the right bit of the probability distribution. But if I did that same kind of motion here, I might get a bit which has almost zero probability being mapped into a bit which has got a high probability. And that's not going to be the same probability distribution, obviously. So it could well be that the world is constituted by states, ontic states, each of which can be, falls under the support of some operational eigenstate, which is the sort of macroscopic ways of what things can be. But it's not the case that all probability distributions over those ontic states are ones that can be, ones which are operational eigenstates. And for the cognoscenti, there's a concrete example of that, and it's given by the two-dimensional Edinburgh model that Koch and Specker had in their 1967 paper. So that's a case in which all the ontic states are ones which can be accessed by my operational eigenstate preparations, but not all the probability distributions are mixtures of operational eigenstate distributions. The other kind of view, and this is the kind of view which corresponds to the de Broglie-Bohm theory, is one which says, yes, all of my ontic states are still macro-definite. I suppose I should have still had L and R here. But that there are some ontic states which are still macro-definite for L and R, but that when I prepare my system in an operational eigenstate, I can't get into this region. So the operational eigenstates are restricted to probability distributions over here or here. There are definite ways the world are specifying left or right will be my result when I do the measurement over here, but these aren't ones that I can prepare. These are ones that I can only evolve into when I have some general evolution. And this is, as I say, this is like what happens in the de Broglie-Bohm theory. And in these cases, it'll be the case that all the probability distributions that I can produce over here always give some non-zero chance for getting a left versus a right outcome. So for these, the reason that these aren't in the operational eigenstates is whenever I try and access any of these ontic states, I can only do so by a probability distribution which is smeared across the left and the right ones. So I can never get just pure left or pure right, which is what I need for an operational eigenstate. It's either got to be probability distribution just over the left or probability distribution just over the right. And again, these are ones that I've simply not tested for whether or not they're disturbing by doing my setup like this, because I only tested for the operational eigenstates. Because the operational eigenstates correspond to the intuitive thought about how macroscopic things behave. At least they correspond to how macroscopic things behave when you're looking at them. Okay. We might be left with a remaining puzzle. That's all very well and good, but I can see that there were formal get-outs maybe, but I just don't understand how my null result measurement is disturbing. Okay. I think this is what's going to Leggett and Gard might still say at this point. And there's a very revealing passage in one of their discussions a couple of years after their original paper where people were moaning in various more or less coherent ways about how they were unconvinced by Leggett and Gard's discussion. And they come up with this quite punchy but very revealing statement. They say, look, should anyone wish to interpret the results of our proposed experiment, which assumed for present purposes agree with quantum mechanics, by saying that the macroscopic object is indeed in a definite macroscopic state? And that's what I'm saying here. We're saying, look, all of the ontic states available are macro-definite states. But it's nevertheless physically affected by an interaction which we know could have occurred only if it had been in a different macrostate. Well, look, you're free to say that if you want to, but we leave it to the reader to judge whether or not such an interpretation in any way diminishes the force of the puzzles that we face, essentially. And that's kind of persuasive until you look carefully at what it says in red. You know, the thing is physically affected by an interaction which we know could have occurred only if the system had been in the other macroscopic state. And the question is, well, look, how are we supposed to know that? That's not something which is experimentally available to us. And indeed, that's the force, essentially, of this whole discussion that I've been giving you for the last 20 minutes. You know, you might have some theory which leads you to believe that, in fact, the two couldn't interact, and they only interact when things in one state. But do we have any neutral way of testing that fact? Answer, no. All we can do is this kind of operational procedure, which I've sketched so far. So it's simply not the case that we know this, and to think that we do is to push oneself into a non-model independent framework again. It's to move us away from the strength of the Bellian methodology. Okay, so to conclude, sorry to have gone on so long. So one straightforward and possibly not terribly interesting conclusion here is that macroscopic realism is potentially ill-named or slightly misleadingly named because there are plenty of other and perhaps better motivated forms of realism that one could have in quantum theory, which give us realism about the macroscopic without being macroscopic realist. Notwithstanding that, we can give an operationally well-motivated model-independent framework for these kinds of experiments, as I've sketched. And when we do this carefully, we see that it's not actually the case that the Leggett-Garg inequality violation is testing the failure, holding, I suppose, of macroscopic realism. It's testing something weaker. It's testing what we call operational eigenstate macroscopic realism, which is the view that all the ways that the world are can be given by statistical mixtures of operational eigenstates. That's quite a natural view. That amounts to the view, remembering what operational eigenstates are, it amounts to the view that the world behaves, the macroscopic world behaves in the same way when we're not looking at it as it does when we're looking at it. Because when we look at it, systems are in operational eigenstates. Now, I know that the table is over there. I don't know what the details of its microstates are. There's some probability distribution over those microstates, but I know that if I look at it again before it's had a chance to evolve, then I'll get the same measurement out again. Okay. When I'm not looking, don't necessarily know how the world behaves, but it's perfectly natural to say that when we're not looking, it behaves in the same way as when we are looking. So it's not true that Leggett-Garg inequality violation tests, if you like, the big metaphysical claim of whether or not microscopic realism is true, but it does still test this quite interesting, perhaps epistemic come metaphysical claim that the world behaves in the same way when we're not looking at it as it does when we do. Okay, I think that's everything that I want to say. And if that was all too quick, we've got a very long paper which says it all in words of one or more syllables. Thank you.